Hello everyone, my name is Wang. I'm pleased to present our work that has just been accepted by ACM Multimedia 2022. The title is You'll Only Hypothesize Once, Point Cloud Registration with Rotation-equivariant Descriptors. In this paper, we focus on the feature-based point cloud registration problem, which typically consists of 4 steps: feature detection, feature description, feature matching, and transformation examination. Specifically, feature detection is in charge of detecting repeatable key points, on which feature description will extract discriminative descriptors, and the learned descriptors need to be invariant to the unknown rotations. Then feature matching will match these descriptors to find reliable correspondences. Finally, the correspondences are used in transformation examination. Generally, cabbage algorithm will be used to generate a set of hypotheses for forensic verification to find the final output rigid transformation. Yoho makes improvements in feature description by constructing stronger descriptors, and in transformation examination by examining robust hypotheses. Let's start with our motivations. For feature description, the existing descriptors typically rely on 3 ways to obtain rotation invariance. Most of them extract a local patch of a point by radius searching. Then, a local reference framework representing the local orientation is constructed by the principal component analyze algorithm. The local patch is aligned to the calculated local reference framework to make the patch losing its orientation information. Finally, the rotation invariant features can be extracted based on the aligned patch. However, the local reference framework is sensitive to noise and point density variance. The unstable local reference framework causes unstable patch alignment and unreliable rotation invariant descriptors. It means that using local reference framework to lose orientation information is unreliable. Some other methods resort to data augmentation or handcrafted descriptors that has been proved to be less generalizable or discriminative. Thus, the rotation invariant descriptor construction is still a challenging problem. For transformation examination, the existing methods mostly resort to cabbage algorithm to generate transformations. It needs at least 3 correspondences to compute one transformation. Then if we obtain 100 correspondences after feature matching and there are only 10% of them are correct, then we can generate a million hypotheses and only 0.1% of them is correct. The searching space of transformation is too large and contains too many superior ones in them. It causes registration fails quite easily. We propose that we can solve the above problems by merely encoding the orientation information to descriptors. Our solution can be summarized as follows. First, given the extracted local patches, we encode their shape and orientation information to their descriptors. The shape information is rotation invariant, while the orientation information will change as the point cloud rotating. Thus, we propose to decode the shape information of the descriptors for feature matching, which is free of local reference framework and guaranteed. Also, we further utilize the orientation information to align the paired local patches, which is exactly the same as the global transformation. Thus, we can obtain rotation-invariant features with theoretical guarantees, and we can generate a transformation utilizing only one correspondence. It means given 100 matched correspondences, with 10% of them are correct, the searching space of ransack will only be 100, and nearly 10% of them will be correct. Then we will introduce how we realize it. Our descriptor, called Yoho disk, is constructed on icosahedral group. It is the largest subgroup of rotation group and contains 60 rotations. Then given a patch, we first rotate it using the group and obtain 60 rotated copies. We extract features on the copies using the same backbone network and obtain 60 n-dimension features. It is denoted as a 60 times n matrix. Then we propose to strengthen the features by stacked group convolutions to identify the pattern defined on group. The group convolution is conducted on the 13 group neighborhoods shown in the figure. The strengthened features is our descriptor Yoho disk, which is also a 60 times n matrix. The key observation of Yoho disk is that it is group rotation equivariant. It can be mathematically proved from the closure property of the group. If we apply a group rotation to the point cloud, its Yoho disk will only have a change of rule permutation. An example is shown in figure. The left is the point cloud, and the right is Yoho disk. There are 60 squares, means 60 rows of Yoho disk, and each row of Yoho disk have different values, means different colors here. And if we route the point cloud using rotations in the group, the color will not change, but the location change. It means the row permutation of Yoho disk. However, such a row permutation can be easily eliminated by a polling operation to obtain rotation-invariant descriptors. Though the rotation invariance is not strictly invariant to the rotations outside the icosahedral group, the existing rotation invariance already provides a strong inductive bias for the network to learn invariance to other rotations. For feature matching. After feature matching, given a pair of Yoho disks, we can decode a rotation from their rotation equivariance. If the rotation is in the group, we can simply retrieve it by finding the permutation that best aligns the paired Yoho disk. Well, for the other rotations, we propose a cost-to-find strategy. We first define a cost rotation as the group element that is closest to the real rotation. It can be calculated by retrieving the best alignment permutation. However, due to the residual between the real rotation and the cost rotation, the paired Yoho disk cannot exactly align by the cost rotation. Thus, we can regress it by the costly aligned Yoho disk pair. It means the alignment residual indicates the residual between the cost rotation and the real rotation. And the final rotation can be the multiplication of the cost rotation and the regressed rotation residual. Finally, we propose two ransack variants to resolve the superior's hypothesis. Firstly, we can also use cabbage algorithm, but instead of randomly selecting all correspondence triplets to compute transformations, we limit feasible correspondence triplets to the ones with the same cost rotations. Such a verification greatly reduces the searching space to find the correct transformation. Also, we can eliminate a rotation on one correspondence, and we can further compute the translation vector using their coordinates. We propose U-O to generate a transformation on each correspondence, which is a linear searching space with much fewer false transformations. The final pipeline of U-O is shown as below. Given two partial point clouds to be aligned, U-O disk is constructed on point cloud sparingly and is matched to build correspondences. On every correspondence, a coarse rotation and a refined rotation are eliminated, which are further utilized by modified ransack algorithms to find correct transformations. We test U-O on 4 widely used datasets. On 3D match and 3D low match, the rotation invariance of U-O disk is distinctive enough to achieve a higher inline ratio for registration recall. With 50 times fewer ransack iterations, U-O outperforms all baselines, which mainly come from U-O's utilization of rotation equivariance to reduce the searching space and superior solutions. As a descriptor, U-O owns strong generalization abilities with less cost on computation time due to the inherent rotation invariance and the equivariance with theoretical guarantees. We also conduct ablation studies on our designs. Firstly, we compare the rotation invariance from the backbone and the group pooling. The group invariance is more distinctive to achieve better registration performance. Then we show that using coarse rotation as a simple filter to select correspondence triplets can yield stronger registration performance by resolving many superior transformations. Then, the group convolution enables the network to exploit patterns defined on the icosahedral group, which brings about 4.9% improvements on the feature matching recall and 9.6% improvements on the registration recall. Finally, U-O achieves the best performance and shows the effectiveness of our rotation equivariant designs. When adding noise and density variance to point cloud, the rotation invariance from group pooling performs better than the local reference framework-based invariance. We also show that by reducing the transformation searching space, we can find at least one correct transformation using up to 500 ransack iterations only, while the existing methods typically need much more iterations. Here are some qualitative results of U-O on the 4 datasets, and a video of ransack transformation searching. U-O can find a correct transformation much faster. The code has been open source and welcome to use it. Thank you.